Okay, good morning. We're going to start this demo event of the FirEUrisk. I wonder if the online people is listening me well. Please, could you react on that? Anyone? Okay. Um, we are here as the series of demo events that are part of the FirEUrisk H2020 European project. We started 3 years and a half ago, so we are in the last 6 months of the project. Um, Domingos Viegas, the general coordinator, is with me now. He will start this session by presenting the general lines of the project, and then I will briefly mention the integration framework that we have developed for putting together all the variables related to fire risk, which also are part of the fire mitigation and fire adaptation. Then we will start presenting the different products by the main authors of them, following by an analysis of how these different variables are integrated and how they will be used also for mitigation and adaptation purposes. Um, Before starting, I would like to thank Lucrecia for organizing this meeting, all the details and the logistics. Just briefly, I would like to remind the presenters to be very strict about the allocated time, so we don't have delays in the general agenda, particularly taking into account that many or most of the people are online. The questions, in principle, will be answered by Zoom, the functionality of Zoom that all of you have received, how to deal with that. In case we have a few minutes after the presentation, we may have questions here, but not online because there are too many people. Um, all are welcome to make questions through the functionality of Zoom, question and answers. And product cards are a description of the products that will be presented here, along with the contact person for further information. I have a few copies, printed copies, in case any of you want to take it. And of course, all of you that are present here, you are more than welcome to discuss with the presenters during the coffee breaks and lunch. The presentations will be sent, make available to all of you through the web page of the project. Again, the general coordinator of the project is Domingos Viegas, who is a professor in mechanical engineering at the University of Coimbra in Adai. Long experience with forest fires. I will give him the room. Thank you.
Thank you, Emilio, and good morning. And good morning to everyone who is present, and also to those that are attending online. If you allow me, before even I start my presentation, I should like to tell you I'm from Portugal, as you can see, and I've just heard bad news that come from my country. Today, it's a very bad day for fires in Portugal. It has been these days, and unfortunately, it will be apparently next days. And I've just heard that a firefighter was killed in a fire this morning. So if you allow me, I would like to ask all of us to stand and keep a minute of silence in homage to this person and to all those who die and lose their lives in the fires. I'd like to start thanking all of you that are here, and also to my colleagues who organized this event, particularly to my colleague. Uh, Particularly to my colleague, Emilio Chuvieco, who is the scientific coordinator of the project, and he organized this event with his team. I'm going to make a general presentation of the project, and Emilio will then make, let's say, more technical assessment of the products that we developed. I welcome all of you to this demo, and particularly to those of you that came on purpose, and I know that some of you came on purpose for this event. The FirEUrisk project developed extensive research during 3.5 years. It's a 4-year project. And our 3 main words were these: risk assessment, risk reduction, and risk adaptation. So you'll hear these 3 concepts during today. We planned 6 events to demonstrate the applicability of our results, and this is the last one. It is applied to the entire Europe. And these demonstrations were held in different places. We had 5 pilot sites in Catalonia, Central Europe, Portugal, Greece, and Sweden. And we started them already 1 year ago. He needs to get the voice up. I'm sorry, we are fixing a problem with the micro. Yes. Can you hear me now better? How is this? Okay, let me see. Yes. Yeah, the presentation. Okay, these demos were held by us quite early in the project, while we did not have, let's say, all products, I'd say, finished. So they were a great challenge for us, but it was rewarding because the organization of these events somehow forced us to achieve results and to make solutions for the different problems. We call the outcomes of the project as products because we want to have things that can be applied operationally, not just scientific documents, scientific results, but things that can be used. As I said, this is a 4-year project, and we are now 6 months from the end. So most of our activities are finished and we are concluding with these demos. The project is quite big. We have more than 38 partners from 18 different countries, many institutions, and also from people from different disciplines that worked in the project. The project was coordinated by the steering committee, myself, Emilio Chuvieco, and 2 other colleagues that helped us in the coordination. And the aims, the objectives of the project were this: to expand the capabilities of risk assessment, to reduce current fire risk conditions, especially having in mind the very large fires, and adapt to fire management strategies to the future conditions, because we know that the climate and socioeconomic environment will be different. And all of this we were pushed to do in an integrated way. Let's say, not to do things separately, not to work with institutions separately, but put everything together. This is the overall diagram of the project. And there you'll see always these 3 concepts: assessment, reduction, and adaptation. This was our leitmotif to work in the project. And in risk assessment, we, from the beginning, wanted to go beyond the concept of fire danger, because people sometimes speak of risk of fire as something due to meteorology, but it has many dimensions. We introduced the concept of vulnerability. We looked at the socioeconomic conditions and ecology, and we aimed at the wild and urban interface areas, because that's where people are and where accidents can occur. And we are also asked to involve every sector, including the local population. In risk reduction, we looked at different reduction strategies. We looked at the reduction of human-caused ignitions, and also to improve the socio-ecological resilience and capacity building. We studied extreme fire behavior and analyzed some extreme fires that occurred in Europe in the past years. And we gave guidelines to improve the training of all stakeholders. And in adaptation, we looked at the future fire regimes and climate conditions, and studied how these risk change drivers can work in future scenarios, and how we would be prepared to face these new fire-prone regions, because we see that the high altitude and northern areas of Europe are having problems that they did not have a couple of years ago. And again, the resilience of the wild and urban interface in relation to wildfire, extreme wildfires. And this all we were asked to do in an integrated form, and working with everybody, with the communities, with institutions, using all tools that are available, and also look at cascading effects that can result from wildfires, and networking with the research community. We have created several boards. One of them is the FirEUrisk Observatory, and I'm happy to greet Mr. David Thomas from the observatory, who came from Portugal to attend this meeting, and working with the other institutions of Europe who are also present in this meeting. We have in our program these 5 pilot sites where we did these demos, and we also had demonstration areas where we showed some of the products of the project at a smaller scale, I'd say. And this is where we are now today, showing that the results of the project can be applied to all places in Europe. We know that Europe is very different. There are many specific problems, but we try to adapt our solutions to different regions. As I mentioned, we did some reports on the wildfires that occurred in 2021, 2022. These are 2 reports that we published together with the GRC and are available online. And the report on the fires of 2023 is now being concluded. One of the goals of our project is to develop a roadmap for an integrated wildfire management strategy for Europe. And this diagram, let's say, somehow encapsulates our ideas, because we propose that we should have a scientific strategy for which the project is working and has been working. And there should be a management framework. It's a series of principles, goals, guidelines, and processes adopted by everyone, and governance and policies that need to be developed in each region, in each country, and also at level of Europe. We feel that European Union does not have a general policy, a general goal, general governance for the problem. We are addressing the problem for many years, but let's say by bits and pieces, and we want to propose some guidelines to modify this situation. And this is, in a nutshell, what I wanted to say about the situation of the project. Now I give the word to Emilio to present the results. Please, Emilio.
Okay, thank you, Domingos. As I said before, we are going to present you the main products that we have developed within the project. And we thought it would be useful to first reflect on the general scheme that we have developed to locate all these small pieces. As Domingo was saying, this is a large project. We have 37 partners. You can imagine it's quite difficult to coordinate all them from many different countries and different backgrounds. So the basic idea is around these three aspects of wildfire risk: danger, exposure, and vulnerability. There is a high discussion in the different thematic groups working with different disasters on whether exposure is part of vulnerability or not. Well, at the end, we decided to consider as a different part, different section, but we can mostly focus on danger and vulnerability. Danger is well developed. Most existing fire risk assessment systems include these variables. Maybe not that much the human aspects, but for sure the fuels, terrain, and weather are part of there. And vulnerability is not that mature. There are still many systems that really do not consider that. And we, of course, consider this is very important. And actually, most of the natural hazards is one of the main issues that they consider, because in many natural hazards, as volcano eruptions or earthquakes, we cannot act on danger, on the physical probability that something occurs, but rather on vulnerability in trying to reduce the negative impacts of that natural hazards on people and natural ecosystems. The project is organized around three work packages. The first one is mainly dealing with the assessment of risk conditions in current situation. The second is on risk reduction, mainly targeting to reduce those factors that are more relevant in the starting or developing of fires. And risk adaptation is mainly considering future conditions, mostly based on climate models, but also on land use models, because both aspects are very important, not just how the weather is going to change, but also how the land use is going to change, because fires obviously is an interaction between weather and social structure, social issues. And then all these three work packages are meant to be integrated in the work package 4, which also include cascading effects. And then demonstration work package is actually dealing with this type of activity as we are now. And dissemination is mostly considering how the project can be better knowledge and better used by end users. There is a group on a scientific forum, a group on end users, and of course, we also trying to disseminate through academic events. All these, again, all these components of the FirEUrisk risk assessment system will be reviewed today. As you will notice in the agenda, we will have 3 assessment periods in which we are going to ask your opinion about how we did generate these variables, whether you consider they are sound approaches to those variables, and how the they are integrated. That will be after lunch, basically. So I really appreciate your opinion on this. Is one of the main goals of this activity is to know the opinion of users about what we have done. We already obviously have exchanged ideas with users from our different countries involved related to fire, but of course your opinion also will be very, very useful. The scheme that we are going to work on around this along throughout the day has been published last year in an open access journal called FIRE. You have the paper available. We are quite happy about this paper because it was done by most of the groups involved in the project. I think there are 27 authors in the paper, and has been very well accepted by the community in 1 year. We have more than 9,000 visualizations of the paper, more than 30 quotations in scientific papers, and it has been elected as one of the editors. It's 5 out of 400 papers that they have published. And so I think that was, in our opinion, a good contribution of the project, because we have a lot of literature review in the paper and a lot of thought on potential ideas to integrate all these products, which is obviously quite a challenge because the variables that we need to consider are quite diverse, very different, and therefore putting them together in single indices is quite a challenge. Okay, so this would be my introductory part. I hope that will be useful to locate yourself in what we are going to review. It will be, I think, about 14 presentations, so I hope you will not lose yourself. But if you do, please ask us during the coffee breaks or whatever. We are very happy to help you on that. So with that, I will introduce the first speaker, Clara, on human ignition. ¿Quieres estar de pie?
Hello, everyone. Can you hear me? Yeah. So my name is Clara Ochoa, and I'll be presenting the product on likelihood of human ignitions. So first, I'll walk you through the dependent and independent variables that we use to train the model, but also to predict the likelihood. Then I'll show you some of the models that we tested, and then, of course, the results and some conclusions. As a small reminder, the human ignitions falls within the danger part, the danger component of risk. And within the framework of the model, we focus mainly on large fire across Europe to aiming to identify the main important drivers of ignition at a continental scale. So here you can see the cartographic representation of the dependent variable. This map shows in red the historical data of ignitions across Europe, and it's for the period 2001 to 2019, and it derived from the FirEUrisk pixel-based burn area. Since we are focused mainly on large fires, we excluded all ignition points that produce burn areas smaller than 100 hectares. Also, those ignition points located in croplands and in urban areas, except for those that were within 5 meters from forest, grassland, and shrubland. We can already see in this representation, some of the ignition patterns that we have in Europe. Actually, it's really bad to see, but we can see that most of them are spread in the Mediterranean, and we have also some patterns in the northern of Europe that we cannot see right now here, but trust me, they are there, and they are important also to take into account. So we compile a comprehensive set of potential fire ignitions variables. We selected based on the availability at 1 kilometer or finer, and that covered the entire territory. Here, I cannot stress enough how difficult it was to find variables that covered the entire territory and that had a resolution, because of course we do have in whole Europe data sets that are for regional scale, but homogeneous for the GANS territory was very difficult to find. So we have here, for instance, distance to secondary roads, which was a variable that we use to reflect the accessibility to isolated areas, because we hypothesized that large fires are occurring in areas where we are not able to access fast enough so that we can stop the spread. Then we have variables that are related to land use, such as interfaces, forest agricultural interface, or wildland forest interface. Then we have also grazing, which was intended to represent the fuel load control praxis, and also a bit of the isolated areas. And we have also demographic variables, such as the population density, especially the one over 65 years that was intended to represent land abandonment and also the impact of an aging population in fire risk. We've also included some climatic variables, such as evapotranspiration and aridity. Here we have also the bioclimate variable, which it was a categorical variable, and the model that we used don't really handle this type of variables. So we separated it in 3 binary variables, which was cool, cold, and warm. And then the ecological regions, we use it just to stratify the selection of the training data. So we have a really good sample of the whole territory for the prediction. So we tested in total 6 models, but for the project, these 3 are the most important. We have the climatic model, the human, and the mixed. From those, the most important, the one that had the better prediction was the mixed model. Even when showing the results of the probability, we saw that the climatic model, using only climatic variables, was overestimating the probability in the Mediterranean and underestimating the probability in Northern Europe, meaning that we had very high probabilities all across the Mediterranean and almost 0 probability in the north of Europe, which was not what we were expecting, because the historical data shows that we do have fires also in the north of Europe. Then we saw the results of the human model, and it failed completely to do any accurate prediction. The probability was all over the place. We couldn't see any patterns of the historical data. And then lastly, we had the mixed model, which was the one that actually predicted the probability really good in the south and in the north of Europe, and therefore the best for the project. So here I will show you only the results of the mixed model because it's the product that we use for the project. But if you want to see the results of the other models, you can check the paper that is also listed. So here we have on the left the cartographic representation of the probability of human ignitions. We can see that the probability is higher in the Mediterranean, of course, because we have these patterns that we saw before in the predicting variable. And we also see these patterns in the north that I told you before that they were there, that we couldn't see it really good in the other map. So on the right, we have a graphic of importance, which is from top to bottom, the most important variables for the model to do the prediction of the probability. We see, of course, that the climatic variables are the most important for the model. This is because, so as I told you before, the human model failed to recognize the patterns in Europe. So when we added the climatic variables, the model was able to separate the Northern Europe from the Southern Europe. And this way it was easier for the model to find the patterns of the human variables and do a better prediction. But we can see from here already that, for instance, we see that the grazing, which was intended to represent the control of fuel, has a negative correlation. So we know that in areas where we have grazing, we have less probability of ignitions, also in areas with high population densities. And then we know that in areas with wildland forest interface or wildland agricultural interface, far away from roads, with an aging population, are areas where we have a higher probability of ignition. So now, I know that this is just a small piece of a larger image, but with this research, we already we enhance the fire risk understanding, because we know where are the higher probabilities, where are fires occurring, which are the variables that can reduce the probability of ignition, and also that can increase the probability of ignition. So if you have any question, you can ask later on in the set of questions, and I'll thank you very much for your attention, and I'll leave the floor to Iveni, no?
We actually have a couple of minutes for questions if anyone has in the room. Yeah.
Okay.
Good morning. Thank you. My name is Claudio Rossi from Links Foundation in Torino. I miss the definition of the task here, meaning what exactly the random forest model is trying to predict. So I guess that it would be if a given pixel of the grid will be on fire or not, will include a fire or not within the season. Is that what are you trying to? So it's a binary classifier for the season, but the temporal range is the season or what?
No, it's the complete year. It's from 2001 to 2019, the whole year without seasons. We take into account the...
So year by year,
No, actually, one binary thing from the complete gap year. So the complete year. So 2001 to 2019.
So if in 18 years that particular point was born at least once, this is the definition.
Yeah, it is working. I thought it was not. Okay, but you have to use it really. Okay, so the dependent variable is a binary raster, or it's where a ignition point occurred between 2001 to 2019. But since we use the whole set of years, it means that this pixel burned once or more in this period of time.
Yeah, then the following comment about the following question would be, then how you divided the training data? Because in this case, I mean, random forest is well known is a prone to overfitting, and so if this is the task in this entire year in the past, then you didn't comment about how you split the data into train, test,
I think
evaluate.
went into technical data because
It's very relevant for
it.
understanding the validity of the results.
Yeah, okay, so we divided into 20 and 80, 20% being the test data, and then 80% the training data. And since the variables that we use, they are also static, we couldn't really use each year because we don't have variables also that represent each year. And so the variables are also, the independent variables are also variables that are settled within this range of years. And for the selection of training data, we use all the ignition points, and then for the absent points, we use different methods. You can see in the paper the different methods that we tested for the training to avoid precisely overfitting. And the best for the project, or the mixed model that was the best resulting model, used the stratify selection of training data, which was using the ecological region, so that we take a good amount of, we selected points from the whole territory to represent all the territory in the training data.
Okay.
Point,
okay, then we can take it offline.
But it was good. Yeah, the
yeah.
complete.
Thank you.
Thank you.
Wait, if we have a minute, we have a question for you online. We don't have a minute. Okay, we will answer it in our session, our question and answer session.
Okay. Okay, let's continue with the presentations. The next one is Eugenie Kandachev. He's a researcher from the Finnish Meteorological Institute in Finland, and he has worked on natural ignition probability. Eugenie, are you there? Whenever you want. Eugenie, we can hear you.
Jenny, we cannot hear you. Eugenie, we cannot hear you.
Can you hear me now?
Yes, thank you.
Is the sound quality good enough?
Yes, thank you.
All right, thank you. Thank you for the introduction, and sorry I could not attend the meeting in person, but let's see what I can do remotely. So I will talk about the development of a predictive model estimating the natural ignition probability. Next slide, please. As you can see from the project integration scheme, our contribution lies at the very foundation, meaning that the task we took had to be approached with extreme care, as any inaccuracies introduced at this initial step would propagate quickly through the subsequent stages. Next slide, please. So when you think about how wildfires start, where and when they occur, we know that the most of ignited fires are in areas accessible to people and when the weather conditions permit. However, sometimes weather alone is enough. And in most cases, the nature of this natural ignition, the lightning is a primary cause. So our task within the FirEUrisk project, or well, the tasks I'm presenting today specifically, was to develop the model that covers the natural ignition mechanism of wildfires. And we approached this problem statistically, deciding to develop a predictive model based on machine learning methods. So our plan was to train the model by combining data from CO2 measurements, remote sensing, and numerical weather prediction models. So this way we establish a statistically sound connection between these MVP outputs and real-world observations, allowing us to predict future observations only using numerical weather prediction model forecasts. Next slide, please. The lightning parameterization, or all the lightning parameterizations, are relative new developments for numerical weather prediction models. Fortunately, the European Center for Medium Range Weather Forecasts, or shortly ECMWF, has recently introduced one of its these parameterizations in its integrated forecasting system, or IFS operational model. This parameterization estimates total lightning flash density based on linear dependence on the square root of Keep convective available potential energy and the charging rate from collisions between meteors in the charge separation region. And this charging rate in its turn depends on the vertical profile of frozen precipitation and the cloud condensate profile within the convective updraft. And all these parameters are available in IFS as outputs. So you can see the schematic illustration of this parameterization on the right-hand side of the slide. and the total lighting flash density has been routinely available as a product of the IFS model since mid-2018. Next slide, please. So first, we compared the model output with both in situ and satellite observations. And interestingly, the modeled lighting flash density showed a stronger correlation with in situ observations. I would say that it might be explained by the model being less sensitive to the detection limit of satellites, but that's a debatable argument. But here you may see an example of such comparison for Sweden in early May 2020. And I'm sorry, we've missed this slide, or it was not attentive. So yeah, here you may see an example of comparison of this modeled lightning flash density and in situ observations of fires caused by lightnings. Next slide, please. So next step was to establish the cloud to ground lightning flash density parameter to estimate it, or in other words, the fraction of lightnings that reach the Earth's surface. And to achieve this, we employed the parameterization proposed by Kufman, I guess, right spelling, and co-authors. And this method did not require additional meteorological parameters, as it is primarily driven by the temperature and water content vertical profiles. And these parameters are already available in IFS outputs. As you may see in the animation on the right side of the slide, we produced a smooth continuous field which would serve well as a predictor to our forecast model. Next slide, please. A few words about the forecasting model we developed. It is well known that in different countries under varying geographical conditions and terrain, the relationship between weather and fire regimes can differ differently. Therefore, for the model, each grid cell and land use type must be treated independently, and we did that. By taking this approach and considering meteorology as a sole driver for fires, assuming that the model training will account for the ignition characteristics of each location, the challenge becomes handling the non-linear, non-stationary, and no-Gaussian processes governing the dependencies between fires and weather. So to address this, we pre-processed the data before fitting the main model. And this involved several steps, including data normalization, homogenization, reducing non-stationarity, linearization, and so on. In other words, a rather lengthy data processing chain is necessary before we can obtain fire radiative power, or FRP, as a main model output. It is worth to mention that we found out that the lightning ignitions are not that much correlated with human-driven ignitions, and it must be treated as a separate independent predictor. Next slide, please. The model prediction example shown here is for a location in Central Europe. The geographical coordinates are provided in the title, and I guess it corresponds to Central Italy, actually. The calibration interval uses 2 years of MODIS satellite FRP observations, and it is followed by an evaluation using 1 year of MODIS data. In the plot, red dots represent fires observed by MODIS. Small blue dots indicate the MODIS detection limit, and the yellow line represents the model prediction. In this case, fire radiative power is predicted only by meteorology and fire danger indices without explicitly accounting for the lightning. And as you may see, the model performs reasonably well. accurately predicting most of the fires. However, some fires are missed, such as the ones highlighted in the black ellipse. This slide also suggests that extending the training period with more historical that data could likely improve the model accuracy. Next slide, please. So in this plot demonstrates that including cloud-to-ground lighting flash density as an explicit independent predictor significantly improves the model accuracy. The model was able to predict several fires within validation interval that were previously missed, as highlighted by the black ellipse. We believe this indicates the model has gained the ability to predict this lightning-induced wildfires more effectively. Next slide, please. So on this slide, you can see the schematic structure of the trained forecasting model. The model receives all its driving predictors from the numerical weather prediction model. Some predictors such as temperature, relative humidity, or precipitation are available directly from the model, while others need to be derived from the input parameters. And the key feature of this training procedure is that it reads each predictor independently, meaning that each predictor's contribution to total fire radiative power can be considered separately from others. Next slide, please. And if we disregard all predictors except for the lighting flash density, the model would only predict the fires caused by lightnings, or we assume that. However, the principal additivity of different models, such as those predicting human-induced fires, of course, requires careful validation. Next slide, please. After the model was trained, evaluated, and validated, we proceeded with operationalization. We received the necessary inputs from ECMWF around 6 a.m. UTC. This data consists of 5-day forecast at approximately 20 kilometers resolution with 2-hour time steps. And once the data is received, we run our model, and generating our model results is really quick, allowing us to produce forecasts for both fire radiative power and lightning ignition probability at the same spatial and temporal resolution. The lightning ignition probability is then submitted to FirEUrisk data hub for downscaling and further integration. And here you may see an example of such product. So this is basically it. This concludes my presentation. Thank you for your attention, and I'm happy to answer any questions you may have.
Thank you, Eugenie, for your presentation and fishing to the proper time. We have some questions on the chat, but if anyone here in the room wants to have a quick question. No? Okay.
We have a question of from Joanna Wabi in the chat. What does the MODIS detection limit refer to?
This is basically the threshold of the fire radiative power that the satellite might detect at a given weather conditions, meaning that there could be a fire that has lower fire radiative power, but it can't be observed by the satellite. And this is, of course, very important parameter because quite many fires are actually below this detection limit.
Thank you, Jenny.
Thank you, Jenny. Anyone else from the room? Oh, okay, good. So we'll continue with the next variable. We will start dealing with fuels, a very important component, of course, of fire behavior. Now we will present Valerio Pampanoni, which is a postdoctoral researcher in the University of Sapienza in Roma. And he has been dealing with the generation of live fuel moisture content. Valerie?
Thanks, Emilio. I hope you can hear me well. Now, what is live fuel moisture content? Maybe many of you will be more familiar with dead fuel moisture content. In this case, we're dealing with live fuels. And as you can imagine, live fuel moisture content is defined as the weight ratio between leaf water content and leaf dry matter. Just this case, we're dealing with live vegetation. And it is usually expressed as a percentage of water weight to leaf weight. When it comes to the integration scheme, you're starting to become familiar with, of course, we deal with fuel, so we deal with both ignition and propagation, and ultimately with danger. But why do we care about live fuel moisture content? Its role is very important in determining the nature of the interaction of fire with live fuels. It deals with fire ignition, so different levels of live fuel moisture content may determine, or at least concur to determine, if the fire will or will not start. It deals with fire severity, so how strong will the fire be and how far will the fire spread. So it also deals with fire spread. And so you can easily understand how why there is a strong interest in measuring, or at least in estimating, live fuel moisture content. When it comes to measuring live fuel moisture content directly, here I put some images and you can kind of get a clean picture of the process, which is actually a very complicated process. You need to go in the field, you need to gather multiple samples of different species, usually, weigh these samples in the field, bring them back to your laboratory, and dry them in special ovens, and then weigh them again, which takes time and people, and know-how. In addition, if you want to have relevant information throughout the fire season, you also need to do this process multiple times during the fire season, and usually at least with a weekly frequency. Which brings me to my next point. Since this data gathering process is so complicated, what we find out is that the actual field data set of live fuel moisture content are mostly concentrated to a few areas around the world which have the resources and the manpower and the know-how to do so. Here you can see the spatial distribution of global FMC 2.0, which is the actual very recent update to the major live fuel moisture content data set. And you can easily see that most of the data sets are located in Western USA, Western Mediterranean Europe, and Australia, which brings me to my next point. Machine learning is not the solution to all problems. One question that is usually raised is, why don't we use machine learning to estimate this variable? Now, we can estimate live fuel moisture content using machine learning, but if we want to build a global model, a model with global applicability, it is very hard to do so using using machine learning, or at least using only machine learning directly, just because we have this data imbalance, around the world. To give you a better idea of this imbalance, which is not apparent only from this map, I can show you here the actual measurement count of global FMC. In this case, I've removed the top country in terms of raw count of measurements, which is the USA. And you can see the top 10 countries except USA. And it is already apparent that France and Spain account for most of the measurements. If I also include the US, these are the top 5 countries, and you can see that US vastly outnumbers all the other countries. But we still were able to use machine learning for our purposes. I will get back to that later. But the point is, we still need a physical model, a radiative transfer model, if we want to build a globally applicable model, which is what we want to do here, since we want to work at the European level. The slide you can see here is taken from basically what is the state of the art of remotely sensed live fuel moisture content estimates. I won't go into much detail here. This is a global product which was published in 2021 and was based on MODIS, so on NASA imagery. And you can see that it uses the combination of different physical models, radiative transfer models, and that it models 3 different types of vegetation. What we did was basically to build upon this foundation. So we still have 3 fuel classes, but we changed two major things. So first of all, we're using European imagery and two different satellite platforms, which are Sentinel-2 and Sentinel-3. But we're also using machine learning to improve basically the speed, mostly, of the inversion process. So we don't use machine learning directly with field data, but we use machine learning to invert faster the simulated reflectances we obtain from our physical models when we compare them with our satellite image measured reflectances. So we can say that this is kind of a hybrid approach. But the introduction of this random forest model was what basically allowed us to expand to the European scale. Initially, the product was designed only to cover the project pilot sites, but the improvement in inversion speed introduced by the machine learning was what allowed us to cover the entire European territory without using basically any more resources than we did before. Actually, we're using less resources than we did before without losing accuracy, of course. And the product uses basically, as you can imagine, since we work with Sentinel imagery and we work with optical imagery, clouds are an issue. So the daily live field moisture content satellite map you will see is actually a composite of the best observation in the last, basically in a window of 10 days. And what I mean by the best observation is basically I take the most recent cloud-free observations. These are our satellite platforms. This is another, I think, advantage of this product is the fact that we can work at different scales. Of course, we want to cover such a vast scale, such as the continental scale, the European scale. We use Sentinel-3, namely the Sentinel-3 Synergy product, which gives us imagery at a 300-meter resolution, which is pretty good for the European scale, and also gives us updated reflectances, updated observations, basically on a daily basis, so we can have basically daily updates on the state of live field moisture content. But again, if you want to go at a smaller scale, so if you want a higher level on detail, we can still rely on Sentinel-2, on the Sentinel-2 L2A product in particular, and its 10 to 20 meter resolution to get a much better level of detail. Of course, for the smaller scale, such as the municipality or even the wildland urban interface, of course, this comes at the cost of temporal frequency, since we have new observations every 5 days, clouds permitting. So now we'll show you some maps of the latest version of the product, the European scale, of course. And I wanted to cover this fire season specifically, just to give you an idea of what the product looks like on your average summer day during the fire season. This image in particular is the very beginning of the fire season. It's taken on the 1st of June of 2024 at a 300-meter resolution again. You can see that the situation is not that bad. All around Europe seems to be reasonably higher live field moisture content, except southern Spain, southern Portugal, and southern Italy. I will now jump 2 months, so we'll go straight to the 1st of August, and you can see, I hope you can appreciate it from both the room and from your PC if you're following remotely, but basically, as you expect, the situation is worse all over Europe. Now, not only Spain, Portugal, and Italy, are and Greece, of course, are in the state you would expect, so much worse than before. But you can also see very low live field moisture content in southern Romania and in eastern Bulgaria, but in general, all over Europe. Again, 1 month later, so on the 1st of September, as you would expect, the situation is still on a downward trend. So live field moisture content on the 1st of September, at least according to a satellite product, was still decreasing. Now, when it comes to product validation, it's been kind of complicated to validate this product since we decided to use Sentinel imagery, because since Sentinel platforms are relatively young compared to, for instance, MODIS, it's very hard to find recent data sets, or at least data sets which were recent enough for us to use for our validation. But thanks to data provided by FirEUrisk partners, we were able to conduct a first preliminary validation, which was published in 2023. And then this summer at IGARS in Athens, we also discussed a new update using the older version of Global FMC 1.0. And basically with all the data we could use for Global FMC, which, I won't get into detail, but required a lot of pre-processing work. And these, of course, are for you to consult. But maybe more interestingly, I will now show you what the validation procedure looks like, because it's kind of hard to validate satellite products with field data, since we have images and on one side, and we have like basically Excel tables, on another, which usually deal with one single collection point. The site I will show you here is a site in Australia from Global FMC 1.0 in Coppins Crossing Road, where a number of different species are gathered and their life field moisture content is averaged. As you can imagine, the dataset refers to the collection site as a single point. So when we work from satellite, we always have to decide, where actually around that point we have to, compare our results with the field dataset. So what we did was basically to draw a 1 kilometer square around the field collection site. And I will now show you what the coefficient of correlation map looks like. Basically, for each pixels in this image, we've constructed a time series of satellite estimated life field moisture content, and we have compared the time series of each pixel, so the estimated one, with the single field time series we have. So this is also interesting because it gives us an idea of where around the field site the satellite product actually correlates with the field data set. And in this case, you can see that there is a very good correlation in the northwestern corner, decent correlation around the middle and in the east, but basically no correlation in the southern part. And this is very complicated to imagine if you don't see the actual satellite images, because if you take a look at this just from the Google base map, for instance, which is very high resolution, it's very hard to see where you would gather field samples, and to distinguish the different species. So I found that this approach works very well to understand how the different sites are shaped. In conclusion, the product is still being finalized. It's basically still being validated, but thankfully it will be validated with the new, recently published Globe LFMC 2.0 dataset, which actually updates the dataset with new field and more recent field data, which is what we need to validate Sentinel-2 and Sentinel-3 products. The validation will be discussed in a paper, which will be open access and will be, of course, for you to consult. But maybe more interestingly, the dataset will be, of course, made available through the FirEUrisk platform. Here's my email if you want to, take the discussion to a later moment. But of course, I will take your questions now.
Is anyone in the room who wants to say anything? Yeah.
Thanks very much. It was a very interesting presentation, and I think it has got huge validity. My name is Zoltan. I'm from Hungary, and just a remark or a question to you. You used this Sentinel-2 satellite, and you created these live field moisture content maps. And as you put on the 2024 images, and as we were going through the year, I'm working for the Hungarian National Command and Control Center, and we are using SESIS, the European Common European Communication and Information System, where requests are coming from countries when there is a huge fire or any kind of major disaster. And as it's only my remark and observation that as we were going through the year, and you mentioned that the situation was going worse and worse, and I just noticed that these countries, Bulgaria, Northern Macedonia, and Greece, they were asking for help or requests, and you put on the map, and there is a huge correlation with the live fuel moisture content in those countries. So have you done this so-called correlation validation with these requests for assistance within the European civil protection mechanism, or you haven't done it, but I think there is a huge correlation, and it's a very, very good tool you have developed. And I think it's quite reliable, but it's only from my point of view and observation. Thanks very much.
Well, thank you very much. It's very nice to hear that, actually. But as I said before, this is still being validated, so it's not like a product that's ready for operational use. On a let's say more private level, we actually discussed this with our colleagues from Bulgaria, which have seen a very large amount of wildfires this year, an abnormal amount of wildfires, and it actually seemed to correlate pretty well with what we were seeing. And I think there would probably be also multi-year correlation, meaning that probably this year, live fuel moisture content, for instance, in eastern Bulgaria is much lower than it was last year, at least in years where we had the usual amount of fires. But of course, we still haven't taken that to a proper analysis level, and of course, not even to the top operational level, with where it can actually be used for the civil protection. Of course, I hope we will get to the point very soon.
Thank you. Well, just a brief remark is that Valerio is dealing with live fuel moisture content. Of course, dead fuel moisture content is quite relevant, and this is very much extended now in the system fire risk assessment system based on meteorological data. And you refer to EFIS, and we have two representatives from EFIS here. Maybe they can, Duarte, you can comment a little bit whether you have or plan to include this live aspect, because you already somehow estimate the dead fuel by using fire weather index or any other weather index commonly used for danger estimation. So maybe.
Yeah, thank you, Miri. Yeah, we are thinking on including your data or the data derived by the FirEUrisk in our system as well. As Mark was saying, Sasha was saying, yeah, we have, I saw also a good correlation between the UCPM. UCPM is the mechanism that he was saying about the activations that they have in North Macedonia, Albania, Bulgaria as well. And we see a good relationship between the live fuel moisture content and also the activations. But it's something that the data that we still not incorporate in our system, but we are going to do as well.
Yeah, well, another comment on this is that actually one of the targets or the goals of the FirEUrisk project is to help the existing systems, of course, and Europe for us is very important because it's a European project. So the connection with EFIS is very relevant, and that was one of the main motivations of organizing this demo event. So we hope that this, as well as other products that we will be presenting, will be useful for. Okay, so if we have, yeah.
We have an online question from David Green. Has the model for fuel moisture also used VIRS data in place of MODIS?
Not at the moment. We tested it on Sentinel-2 and Sentinel-3. But I think I did a Landsat analysis at some point, so still high resolution, but I still didn't take it to, I didn't use MODIS and VIRS. But of course, the model, the base model is very similar to the one published in 2021, which was already using MODIS. So we expect to get basically very similar results,
We are going to continue the session. We are initiated the analysis of fuels with the live fuel moisture content. Again, the dead fuel moisture content has been used mostly for fire propagation that we will see later on. And now we will focus on the generation of fuel types and fuel models and parameters. And the presenter is Elena Aragoneses. She's a PhD student in my university and finishing her PhD on these issues. Go ahead. Thank you.
Thank you. So, good morning, everyone. My name is Elena Aragoneses, and I'm going to present what we did in the FirEUrisk project regarding fuel types and fuel parameters. So, as we all know, fuels, which are vegetation that can potentially burn, is very important for both fire ignition and fire propagation, and it affects fire danger assessment. When we talk about fuels, we need to distinguish between two concepts. The first one is fuel types, which refers to the categories referring to different vegetation that have similar behavior in fires. And the second concept is fuel parameters, which are the numerical values describing the physical properties of the fuels. Also fuels can be surface fuels or crown fuels. Surface fuels refer to the fuels that are next to the ground in the first layer, whereas crown fuels are the ones referring to the canopies of the trees. Most of the fires in Europe are surface fires because they affect surface fuels. However, the 2% of canopy fires that happen in Europe are the most severe, causing most of the damages. And that is why in our study, we wanted to include both surface and crown fuels. So in order to understand wildfire risk regarding fuels and model fire behavior, we need to have a lot of information regarding fuels. First type of information is referring to fuel types. So the categories referring to the fuel characteristics, and the fuel parameters, which are, as I said before, are the numerical values referring to the physical properties of the fuels. And ideally, we should have information on both surface and canopy fuels. So what we did in the FirEUrisk project was to generate the first full set of information regarding fuels that is intended to be useful for fire behavior understanding and modeling in Europe. More in detail, we generated one fuel type map regarding both surface and crown fuels, one fuel model map referring to surface fuel parameters with the average values of the standard fuel classification system of Scott and Morgan. And because the Scott and Morgan classification system only refers to surface fuels, we had to complement this information by developing 5 maps of custom canopy fuel parameters to have also information on canopy fuels and canopy parameters. And for this, we developed information of canopy height, canopy cover, canopy base height, canopy fuel load, and canopy bulk density, which are the most important canopy fuel parameters in the fire assessment. All of these layers are at 1 kilometer spatial resolution because our intention is not to understand individual fires, but rather to have an overall view of how does fire work at the European scale. And the year for these products is circa 2019-2020. Now I'm going to explain a little bit each of these products, starting for the European fuel type map. For the generation of the European fuel type map, we developed a new fuel classification system, which is the so-called FirEUrisk fuel classification system. This system is new because it is intended to be multi-purpose, so for fire behavior modeling, but also fire propagation, fire emissions, etc., and is hierarchical. This means that depending on the spatial resolution we're working at, on how much detail we need, we can use different disaggregation of field type categories. So the main field type categories would be forest, shrubland, grassland, cropland, wetland, and urban fields. And then if we need more detail for a regional or local scale, we can go into further disaggregation of these field types. This is very important because it allows harmonization of field type mapping in Europe. So for example, if we are working